All right, this is Professor Jay Werber again. I am now going to solve. So this is part 2 of the Haber Bosch example. So problem set 5. Now we're going to solve it. So in the first part, we set up the problem and sort of solved part A, and then talked about how we're going to solve the actual mass balance for this reactor condenser with a recycle and a purge, where the reactor is at equilibrium. Okay. We said for how we're going to solve it. So first we did the overall CV, and then we did this trick where we said that we're going to let the recycle ratio be a variable that we assume is known, and then we solve everything else in terms of the recycle ratio until the very last step, in which case we solve for the recycle ratio. And this is using the equilibrium. So that's sort of the process, and if we want to do this, it's definitely easiest to do it in Excel. So I'm going to do that. So let's go ahead and set up Excel. So I'm going to just start a new Excel file from scratch. Okay, so now we have our Excel file. I'm going to copy in, so as you can see, that was the example that I did it in class in 2022. I'm going to just copy in this guy, the picture, just so we have a good, just so we're very clear as to what the different streams are. Okay, so let's set up our file now. So stream, stream name. So 1, 2, 3, 4, 5, 6, 7. So the stream 1 is the feed. Stream 2 is the reactor feed, or then maybe the reactor inlet. How do we say that? Reactor outlet, or reactor product maybe. And then this is the condensed ammonia. Stream 5 is the uncondensed gases. Stream 6 is the purge, and stream 7 is the recycle. All right, so let's maybe, so I'm gonna just select all. I'm gonna wrap text to make it look a little nicer, and then I'm gonna center and center vertically and sideways. Okay. So now we have the N2, H2, NH3, and total. Right? And so these are all molar flows. And this is in mole per second. Okay. And I'm going to make this gray. Oops, wrong thing. Meant to do this one. Okay, and now I'm going to do mole fractions at the bottom. Oh, I forgot to do inerts. So I'm going to add in one more. Awesome. So I'm going to merge this again. Mole fractions. Awesome. And then lastly, I am going to give this border so it's a little easier to see. Okay, so this is our table. The other sort of things that we kind of need, maybe we can just add it to the side of the table. So the one is the extent of reaction. The other one is the recycle ratio. And the recycle ratio, again, is defined as N7 divided by N1. Okay, so let's start putting in things that we know we solved the overall CV and we solved for the feed. So let's put in the things we know. So the feed was 100 moles per second. We had 4 moles per second of inerts. And when we solve for nitrogen, we had those 24, and there's no ammonia. And the one thing that we have is that the hydrogen is just 3 times that of nitrogen. So I'm going to just set that as a function everywhere. All right, so great. And so now we can do this. And so I'm going to what should I do here? I'm going to have it be there, so the row is fixed. For me, this is hitting function F4, but basically I'm just setting this so that the row is fixed, so that all I need to do is scroll this down in the corner, and now it has the mole fractions all set in the feed. Okay, so that was the feed. The other streams we know are streams 4 and stream 6, right? So let's go see, what do we do for stream 4? And we had the extent of reaction was 22.8. So let's do 22.8 here. Stream 4 we have is 45.6 for ammonia. And the total, all that stuff is 0. I should be able to just copy this over because of how I set it up. So I'm doing that, and perfect, it looks good. And then the purge stream was where? So we still have, let's see, the purge stream, we still have 4 moles of inerts. We have 1.2 moles of nitrogen. Still, for hydrogen, we can just do 3 times. We have 0 moles of ammonia because all of the ammonia is in the condensed stream. I can just sum the rest, and then I can copy this over. And now we get our mole fractions in the purge stream. And of course, these mole fractions are going to be the same in the recycle stream and in the uncondensed gas stream. So I'm actually going to just go ahead and copy that over. So I'm going to copy, and then I'm going to paste special. Actually, I could just do values right here because that's the special that I want to do. So that's the one way to do it, but I'm going to paste special, paste values. Great. So now these are values. These are not functions, unlike the other ones. And this just makes it so we can go the opposite way if we want. Okay, I'm going to have the formatting be okay. Okay, great. So now we have streams 5, 6, and 7. We talked about in the CV, the next step would be to do the splitter here and to do it as a recycle ratio. So the recycle ratio, I'm just going to set a dummy variable. So I'm going to just have it be 50, let's say. Okay, and so 50 is N7 divided by N1. We know N1 already. So we could just have this be, so N7, the total is just the recycle ratio times the total from N1. And it's that simple. And so because stream 5 is just stream 6 plus stream 7, all I got to do is add those together. And then because the mole fractions of all of the species is going to be the same in 5, 6, and 7, all I have to do is multiply this guy. So I'm going to do function F4 again. So that fixes the row. Multiply that by the mole fractions. Okay, so multiplying it by the nitrogen mole fraction. I'm going to scroll this down. Perfect. And I'm going to do the exact, just copy it and put it over here. And yeah. So now we have streams 5 and 7 done, quote unquote, but they're done as a function of the recycle ratio. So they're not quite done yet. But the really nice thing about Excel is that as we change the recycle ratio, this will auto update, right? So if I change this to 20, you know, auto updates. 25, auto updates, which is all good. That's what we want. So I'm gonna make all of this maybe 1 decimal place, just so it doesn't look so terrible. Okay, so now we have streams 5, 6, and 7 done. We need to do stream 2, I guess. And stream 2 is just stream 1 plus stream 7. So I'm just gonna do 1 plus 7 and just scroll it down. And then the mole fraction things should be the same. We should be able to calculate that from stream 1, from the molar flows, just like that. All right, so that's stream 2. That's all done now. And now we need to do the reactor product. And this is the part where it can be a little tricky. So we have, let's see. So let's see. So what I'm going to do for the reactor product is just think of this as an extended reaction sort of thing. So remember we have, I'm just going to write it on the right. So for a typical reaction, you know what, how am I going to do this? I'm going to insert a text box. Okay, so for a typical reaction, we have n sub I is equal to n sub I 0, like the initial one, plus the stoichiometric coefficient times the extended reaction, right? So I'm just going to do that for every single thing. So for the reactor inlet, so basically we want, for nitrogen, we want the initial, and then plus, and then for nitrogen, the stoichiometric coefficient is -1. And I want to do that times the extended reaction. Okay, so that's it for nitrogen. I'm going to do the same thing for hydrogen. Okay, I'm going to do the same thing for nitrogen. So it's 2, it's a stoichiometric coefficient here. Inerts plus 0 times the extended reaction. So that's kind of boring. And then the total is just summing up all of this. Okay, awesome. And then the mole fraction should be, we have the molar flows first, so let's calculate the mole fractions from the molar flows. Great. So now our table looks done. The issue though is that it's all a function of the recycle ratio, and we have no idea whether this is at equilibrium or not. So basically now we need to solve for the equilibrium condition to make sure that everything sort of works out. So, but if we had a fixed recycle ratio, like let's say that you knew that the recycle ratio was 20, but it was not at equilibrium, then we solved it, right? You set the recycle ratio to be 20, you solved everything else as a function of that, and this is done. So that's all good. But we do want it to be at equilibrium, and so how are we going to do that? So the equilibrium function is something we wrote up here that we want to do. So let's have it be this guy, right? So we know KEQ is what? From the problem statement, we have that it's 1.06, so equals 1.06 times 10 caret negative 6. Okay, so it's pretty low KEQ, and our pressure is 200 atmospheres. All right, and so what we can do is then calculate the what was it, the mole fraction of ammonia as a function of all these other things. And this is in stream 3, right? So this is the reactor product. So YNH3, or Y3NH3 from equilibrium, okay? And so what we're going to do is set this as a function of everything else. So we have it as equal to, let me just, how am I going to do this? Okay, so I'm going to write it out over here. So YNH3 is equal to K, this is KQ, times Y N2 times YH2 cubed, and then all of that is to the 1/2 power, and then we're times the pressure. Right, so let's not, where's this? Okay, so let's do that, right? So let's do it as a function of our values in the table. So this is KEQ times YN2 times YH2 cubed. And this is all to the 1/2 power. And then I'm going to multiply by the pressure in atmospheres. And so this is the expected mole fraction of ammonia from equilibrium. So it's 0.019. You can see that it's actually not terribly far off from the value that's in the that's in the table right now. And so now I'm going to sum of errors. So let's do the square error. And so I'm going to do this guy minus this guy, because we're trying to minimize the difference in the mole fractions, squared. Okay. That's the one way I could do it. Let me multiply this by, let's say, 1,000,000, just so we have something that we're going to try and minimize, and it doesn't already look so small. Okay, and so now I am going to just use solver. So I want to change the square error to a minimum by changing the recycle ratio. Okay. So let's hit solve. Ba-bam. And hope for the best. It says it's converged. And how does it look? So now we have, first of all, let's make this not crazy. So now we have the mole fraction of ammonia. Here is 0.01914 something, 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 something. So from the extent of reaction, so not using the equilibrium, and using a recycle ratio in the table, we have the exact same mole fraction as we would expect from the equilibrium condition. So this is it. Problem is essentially solved. Okay. So this is our final table in terms of the actual product here. Let's see, what else did the problem want though? So it says complete a stream table indicating the moles of each component in each stream, although not really moles, it's moles per second, as well as the single pass conversion of the process. So let's do the single pass conversion. I'll just have it here. You know what? I'm going to make this a little bit bigger. Maybe make this one smaller. I'm not sure how it got so big. Okay, so the single pass conversion is looking at the nitrogen consumption in stream 3 compared to stream 2, right? So let's do that. So we have nitrogen, inlet minus the outlet divided by the inlet. So the single pass conversion here is about 6.7%, okay, which is way, way, way less than the overall conversion of 95%, right? So the overall conversion is 95%. But the single pass conversion is just 6.7%. Really, really highlighting. So this is an example where it really highlights the power of a recycle. It also shows, I mean, if you're going to look at the recycle ratio, right? We have the recycle flow is 23 times greater than the feed flow, which is, you know, a lot bigger. So the flows that are sort of are looping back here are quite large compared to your feed. And look at the inerts, right? So the inerts, they come in, they're just 4 moles per second in the feed, 4 moles per second in the purge. But the inert flows in the recycle, because of how much lower the single pass conversion was compared to the overall conversion, the inerts have built up like crazy. And so the molar flows of inerts are about 1,000 or so going back in the recycle compared to just 4 moles per second in the feed and in the purge, which is pretty nuts. So the reactor is going to be pretty big, right? It's going to need to accommodate pretty big molar flows, but the conversion is pretty low, right? 6.7% conversion for a single pass, but then the overall conversion is 95%, which is, you know, pretty substantial. All right, and that is everything for this problem. I hope this video helps.